All right, let's start the next section, which is on marginals and differentials. Um, Marginals and differentials are useful. Let's talk about what they are. Imagine we have f of x. We've got some function, and say that we know what the value is at x. Well, something that is often useful is to know what is the value at x plus 1. Now, if our function is extremely complicated, then it's actually kind of difficult to figure out what the next value is. Or if we're doing computer science, it might take a lot of computer power to figure out the next value. What we can do, interestingly, is save some of that memory by using this approximation. So here's the idea. First, to get the value at f of x plus 1, it's going to approximately be the value at f of x. And that sort of kind of makes sense because it's only the next value in the function. But here's how we can make our approximation be super accurate. What we do is we add the rate of change, the derivative, at that x value. The reason we do that is because we start where we were in the previous point, and then when we add on the derivative kind of points us in the direction of our next point, and that's what can make this approximation extremely accurate. So what we're going to do is go ahead and look at what these differentials are like in a couple examples, and then I think you'll understand it. Another way of writing it is to say that delta y is equal to f prime of x delta x. This is basically just the derivative formula rearranged, but when we do it in this way, we can see very clearly how a change in our x value affects a change in our y value. And so let's go ahead and take a second, and then we will look at an example.